A sudden irregularity has appeared in the multi-instrument tracking of 3I Atlas, measurements that introduce a development in which analysts are flagging for rapid review. 3I Atlas has altered its jet pattern within the same window that its Jupiter trajectory becomes sensitive to minor forces. The overlap is too precise to dismiss without taking further look. And yet, there seems to be a hurdle on the amount of information we're getting from our most advanced observatories. Why? In the past 24 hours, several outlets have repeated the idea that this interstellar object might be dispatching probes to spy on Jupiter, based on a new interpretation of its upcoming trajectory. In this section, we will separate what has actually been observed from what is speculation, using only data backed by published measurements and mission updates. Over the past few months, the object has triggered intense debate. A widely viewed breakdown of the early data pointed out at least a dozen anomalies, including its near-perfect alignment with the plane of the planets, its sequence of close approaches past Mars, Venus, and Earth, its dramatic brightening near perihelion, and an anti-tail that appeared to point toward the Sun. That analysis argued that the pattern of events almost seemed tuned to make the comet observable without ever revealing a sharp image of the nucleus. NASA has now released its best images from Mars orbiters, the Perseverance rover, the Hubble Space Telescope, the James Webb Space Telescope, and new solar missions such as Stereo and Punch. These show 3I Atlas as a bright, fuzzy nucleus wrapped in a dense coma, with short stubs of tail that change direction as the viewing angle and solar wind change. Independent geophysicists have compared these official frames with high-quality stacks obtained by amateur astronomers, who often resolve multiple jets and a clearer anti-tail structure with backyard-class telescopes. Against this background of unusual but still comet-like behavior, a new round of headlines now focuses on Jupiter. A recent article quotes Harvard astrophysicist Avi Loeb, who suggests that the object will pass close enough to Jupiter in March 2026 that small fragments could, in principle, remain bound to the giant planet. He proposes this as a speculative test of an artificial origin, not as an established fact. Mainstream mission teams, including those at NASA and the European Space Agency, continue to treat 3I Atlas as an interstellar comet whose oddities can be studied with standard physics, even if they are not yet fully explained. This trajectory question appears right at the center of the new controversy. The key claim is that 3I Atlas is on a path that would intentionally skim the region where Jupiter can hold on to small objects, as if it were planning to drop off satellites. To understand why this is being discussed, we need to look carefully at the geometry and at what we actually know from orbit calculations. Jupiter dominates the outer solar system. Around the planet, there's a gravitational zone called the Hill sphere, where its pull is stronger than that of the Sun for small bodies moving slowly with respect to the planet. Current solutions of the path of 3I Atlas show that, in mid-March 2026, it will pass near the outer edge of this region. The distance is large in absolute terms, but it is close in orbital mechanics. And it is unusual for an interstellar object that had no reason to care about Jupiter at all. Observers are stating that if 3I Atlas were an artificial craft or a disguised carrier, it could release smaller objects with slightly different velocities as it moves through this region. Those fragments would then have a chance to be captured into long-term orbits around Jupiter, in some cases on paths that existing missions, such as Juno or the future Europa Clipper, could eventually sample. This is not what the data show today. It is a theoretical scenario built on the mathematics of capture inside a Hill sphere. From the purely physical side, the question is whether the comet has shown signs of controlled thrust. Astronomers have measured small, non-gravitational accelerations on 3I Atlas, meaning that its path cannot be explained by gravity alone. The simplest explanation is uneven outgassing, where jets of vapor and dust act like small thrusters and push the nucleus very slightly off a purely gravitational orbit. These jets are visible in amateur images and in stacked spacecraft data, including cases where aligned jets create a short anti-tail that seems to point sunward. For the probe seeding idea to be plausible, those jets would need to be timed and aimed with enormous precision. They would also need to be able to shed fragments with tightly controlled speeds and directions during the Jupiter passage. No current observation has resolved such fragments near the nucleus, and no spacecraft has seen discrete objects peeling away from the main body. The only solid statement at this point is that 3I Atlas will pass through a region where capture is possible, and that a small, unproven set of models explores what might happen if deliberate control were present. This imaging record provides the second pillar for the discussion. The latest NASA releases from missions at Mars and in the inner heliosphere show 3I Atlas as a compact, bright source with a diffuse coma, often with only a short stub of tail. Processing from the Mars Reconnaissance Orbiter high-resolution camera gives a nucleus size between a few hundred meters and a few kilometers across, but the core itself remains unresolved under a thick shell of gas and dust. Hubble data earlier in the apparition gave similar size limits and the same basic structure. At the same time, the Punch and Stereo missions, which normally watch the solar wind, have tracked the interstellar comet as a faint moving knot against the background. Stacked time sequences show a short tail whose apparent direction sometimes flips between pointing roughly away from the sun and leaning toward it. Those flips match changes in viewing geometry and in the flow of charged particles from the sun, rather than any sudden reversal of motion by the comet itself. Amateur observers fill in the gaps. Using half-meter class telescopes and long exposure stacks, they have documented a long ion tail, a shorter dust anti-tail, and multiple jets extending from the coma. In several sequences, the jets appear to fan out and rotate with a period of roughly 16 hours, which is a leading estimate for the spin of the nucleus. These amateur frames often reveal more of the fine structure than the official missions, because they are optimized for deep, narrow fields rather than for broad solar or planetary surveys. Together, these images support a picture in which 3I Atlas is embedded in a dense plasma environment. Ultraviolet observations from the MAVEN orbiter around Mars reveal a bright core region surrounded by a hydrogen cloud tens of thousands of miles across. Spectroscopic data indicate abundant water vapor, carbon dioxide, carbon monoxide, and traces of cyanide and nickel-rich material. This mix resembles a very active comet nucleus, although the exact ratios and the strength of the jets appear to be at the extreme end of known behavior. Most importantly, the combination of changing tail direction, strong jets, and non-gravitational accelerations means that small deviations from a simple orbit are inevitable. These deviations can nudge the path slightly closer to or farther from Jupiter during its future passage, and they are now being folded into updated trajectory solutions. The same data that spark speculation about deliberate control are also used in conservative models that assume nothing more exotic than an unusually active chunk of interstellar ice and rock. This brings us to the core question behind the Jupiter probe headlines. Given the current data, how strong is the case that 3I Atlas is more than a natural interstellar comet? The short answer is that it remains an open hypothesis under discussion by a small group of researchers, while the bulk of the community finds standard explanations adequate, even if some details remain unsolved. Advocates of an artificial origin point to several features. The orbit is almost perfectly aligned with the plane of the planets. The object threads close past Mars and later passes near Jupiter's Hill sphere. It brightened more than expected near perihelion and showed changes in color and tail structure that are not common among known comets. Some commentators argue that this pattern mirrors what humanity would do when sending a probe through another planetary system, using planets for gravity assists and possibly dropping sensors into stable orbits along the way. On the other hand, there are important constraints. No resolved structure has been seen near the nucleus that would indicate rigid components such as panels, booms, or clustered satellites. Radar searches so far have not picked up narrowband radio emissions or repeating patterns that would indicate intentional signaling. The non-gravitational accelerations are well within the range that can be produced by asymmetric outgassing, especially for a body that is small, fast, and strongly illuminated near the sun. Comparisons to earlier interstellar visitors also provide context. Oumuamua showed a strong non-gravitational acceleration with very little detectable coma, which led to suggestions of a thin sheet-like shape or even a light sail. Borisov behaved much more like a standard comet, with a clear dust and gas envelope and a more typical response to solar heating. 3I Atlas sits somewhere between these cases. It clearly has a rich coma and strong jets, yet also shows unusual tail geometry and an orbit that happens to intersect key planetary regions in a way that invites closer study. In practice, astronomers treat extraordinary claims as working ideas that must generate testable predictions. For 3I Atlas, the strongest of these predictions is that if it has seeded probes around Jupiter, then future close studies of the Jovian system might detect small objects on peculiar orbits that cannot be explained by known capture or collision processes. Until such evidence appears, the safest description is that 3I Atlas is an interstellar comet with a set of extreme and unique properties, rather than a space vehicle of unknown intent. This final section focuses on what comes next. The speculative idea of probe seeding around Jupiter only becomes testable if we track 3I Atlas carefully through the rest of its passage and then continue to monitor the giant planet system for years to come. Several active missions and a global network of telescopes are already in place to do that. In the near term, the object is now receding from the Sun after its late October perihelion. It will reach its closest approach to Earth in the second half of December, still far away in absolute terms, but bright enough for professional and advanced amateur instruments. During this window, observers will continue to refine measurements of its brightness, color, jet structure, and non-gravitational accelerations. Any large changes in the shape of the coma or the stability of the tails will feed directly back into updated orbit solutions and into models of the surface. Looking further ahead, the critical milestone is the March 2026 passage past Jupiter. By then, the Juno spacecraft will still be active in polar orbit around the planet, and other missions, such as Lucy and various ground-based radio arrays, will be able to look for any unexpected activity in the wider Jovian environment. These observations are primarily designed to study Jupiter and the solar wind, not to search for alien hardware, but they can still place tight limits on any large fragments that might accompany or follow 3I Atlas. For planetary defense teams and comet physicists, 3I Atlas is already a valuable case study, regardless of its ultimate classification. It samples material formed far beyond our solar system. It challenges existing models of cometary outgassing and plasma interactions, and it tests how quickly we can respond when a fast-moving interstellar visitor appears with only months of warning. The Jupiter encounter simply adds another opportunity to learn, whether the outcome is entirely ordinary or mildly surprising. To summarize, the notion that 3I Atlas is dispatching probes to spy on Jupiter comes from a specific interpretation of its future path, not from direct detection of any artificial objects. The data on hand support a picture of a very active interstellar comet with strong jets, complex plasma tails, and small non-gravitational forces that slightly modify its orbit. Future measurements around its Earth-flyby and its Jupiter passage will either tighten the case for a purely natural explanation or reveal new anomalies that demand fresh models. If you want to keep following those developments, consider subscribing, keeping alerts on for future updates, and sharing this coverage with anyone curious about how real data is used to test bold ideas about interstellar visitors. Thank you for watching and for supporting the channel.